Good afternoon, everyone. Welcome back from the lunch break. I'm Will Hargrave. I have the pleasure of announcing the last sessions today. Before we start, please check all your devices are set to stun, so we're not disturbed by any embarrassing beeps. And please slide into the center of the row so we can, everyone can find somewhere to sit down. Please help the DENOG organization by rating the conference tools and workshops. You'll find the links to everything in this morning's welcome email, which will be in your inbox. You should also have received a link to vote for 3 new candidates for the program committee. So please go ahead and cast your vote for those excellent candidates in the coming days. So our next speaker is Fiona Weber. Fiona is serving as a board member of DENOG in her free time and works as a network engineer at OWDM during the day. In this talk, she will share their journey towards the modern metro network, which started with an effort to modernize the transport network and ended up redesigning everything. Please join me in welcoming Fiona to the stage and enjoy the talk.
Yeah, hello. It's good to be back. Yeah, first about me, as Will said, Fiona Weber. I'm the technical lead at WDZ. I will explain what's that about. But yeah, I have 6 years of professional experience in network engineering, and before that I did some IT security, software development, managed hosting, like all that. First, disclaimer, WDZ, the company I work for, is an RT-Brick partner. We will be talking about RT-Brick a bit, but this is not an ad for RT-Brick. We decided to use the RT-Brick software way before we became a partner, and but I thought it would be good to state that here, so you can, yeah, form your own opinions. WDZ, what? Most people know me working for WOPCOM. WOPCOM is actually the sister company of the company that I work for. We are both owned by the Stadtwerke Wolfsburg, which is the city utility company, so they do all the electric grid, yeah, like what a city utility does. They run buses and so on. The Stadtwerke are owned 100% by the city, and the Stadtwerke owns the WDZ and the WOPCOM. WOPCOM has been founded in the late 90s, first as a telephony provider, later internet provider, and WDZ was a company that was laying around from the old ages, and when I got hired there, we got the opportunity to build up our own consultancy. We do network engineering consulting, most of the network architecture stuff for WOPCOM, but we also have other customers, for example, university networks or internet exchanges. So Freddy of NET7 in his talk yesterday said something along the lines of when you throw the public infrastructure to the capitalist companies, then what you get is essentially the state of fiber rollout in Germany. This is not true for the entirety of Germany. So in Wolfsburg, a few years ago, the city decided that they wanted to have a fiber rollout, as most cities do. And instead of going to some kind of investor-funded company and tell them, hey, please, can you build some fiber network here? They decided to do it themselves and told the Stadtwerke to build a fiber network. So then the Stadtwerke built a fiber-to-the-home network for the whole city. And it is owned by the Stadtwerke, so it is owned by the people. And, well, there are a few layers of politics in between, but essentially the people can decide what to do with their infrastructure. And in that case, they decided they built a network and the Stadtwerke own it. And WOPCOM, the daughter company, the internet provider, telephony provider, they rent the whole network as the whole thing, and they run services on it. And if at some point they decide they want to do something else, they can do that. But for now, this is how it is. You may be asking yourself, where the hell is Wolfsburg? It's there. It's about 1 hour from Berlin. I live in Berlin. Most of my colleagues live in other cities. It's an interesting time with remote work. But yeah, there it is. And let's zoom in and have a look at the network that we have. Yeah, this is our metro region. We also have like a big backbone network that goes all over Germany and some of the Netherlands. But this is the Wolfsburg region. The two green castles are our two data centers, and the dots are our like city pops. The light blue dots are, yeah, this could be a outdoor DSLAM, the boxes sitting at the street corner. This could be a small building. This could be a small pop in the basement of a city building. Anything. And the dark blue dots that are, yeah, we could call them backbone pops or routed pops. Those are the ones where we have routers and where we provide all the services. Talking about services, we have about 30,000 private customers running mostly PPPoE, as one does in Germany, and 2,000 business lines, which is quite a lot, I think, for such a small provider in such a small geographic area, but it's a highly industrialized area, so I guess there are a lot of companies that need services. So most services are 1G or 10G, which is kind of a lie, because after the CPE there is a lot of 100 megabits or even 10 megabits for legacy reasons, but from our side, what matters is 1G, 10G, maybe 25, maybe some services with 100G. Yeah, the area has a radius of about, let's say, 100 kilometers, maybe even a diameter of 100 kilometers. So fiber length is between 2 kilometers and 120 kilometers, which is neat because for most of the fiber connections, we don't need amplifiers. So now you know what I mean when I say a metro network. A lot of people have a different definition, but this is what we call a metro network. Yeah, and a while ago we decided we have to make this. We have to build a new metro network because we replaced our backbone network, we replaced our data center network, and now it was time to do the same for the metro network. Let's have a look at what we got. Some of you may recognize these devices. These are Cisco Metro Ethernet 3000 series. If you have worked with them, I'm sorry for you. They are terrible devices. They are end of life. They are buggy as hell. And well, most of all, they only have 1G access ports. So we have a lot of band-aids to provide 10G services or 100G services. And these devices really need to go. Then for the private customers, we have a totally separate network which consists of ASR 1000 BNGs that we are also using for carrier grade NAT. So yeah, big chassis routers, they have really expensive line cards, so it's not feasible to connect every access switch directly to that router. So we have two 100 gigabit links per BNG, and then we have a Cumulus data center fabric that all the DSLAMs and fiber to the home devices are connected to, and then we tunnel the services to the BNGs. And since the Cumulus switches are data center switches, they are really deep. They are in our two data centers, and we have a lot of optical equipment to bring all the DSLAMs back home into the data centers. So ideally, we want to replace both of these platforms with one. And this can be a challenge. So it is a harsh environment for routers to be placed somewhere in the city, not in a proper data center. We have to deal with low fiber availability. We have some special services that most data center hardware or optical equipment couldn't deliver. Like we need transparent layer 2 services, we need layer 3 VPNs, subscriber management is a thing. I will talk about that later. And since we are talking about a lot of devices, we want them to be as cheap as possible and to be as easy as possible to automate, because we have better things to do than take care of single devices. OK, let's talk about the physical environment we are talking about. This is one of our standard POPs. So you might have seen Eurofiber's talk yesterday, where they built a custom housing. We are not in the position where we can decide what we want to have, because that's what's there. We have a truckload of these concrete buildings and also these outdoor shelters where these lamps are normally in. And the building next to that one is actually a substation, which is owned by our sister company that does the power grid operation. So it's the same kind of building, probably even built by the same company. Let's have a look inside. On the left side, there is a lot of passive infrastructure. We have old copper cables that are still in use. This is Germany, after all. We have a huge amount of fibers that come in. And in the middle of the room, there is an AC unit to keep it cool in the summer and warm in the winter. And on the right side, there is all our active equipment. So we see shelves of media converters in the very bottom. We have a management switch. We have the thing up there is the chassis up there is a DSLAM that also has fiber to the home line cards. And underneath that, there are the routers that are currently providing the business services. And talking about temperature, keeping these isolated buildings on a reasonable temperature is hard and expensive. They have they are just standing there, and the AC unit is fine to keep it reasonably cool in the summer, but it doesn't make sense to keep it at a stable temperature as you would do in a proper data center. So this plot is the temperature graph of just a random device somewhere in the field during summer. This is not the air temperature, but just some random temperature sensor in the device, but it doesn't really matter. Then we have special power requirements. Telco equipment traditionally uses 48 volts power, which makes sense because we just have a few devices, just a few hundred watts, and we need battery backup. So converting the 48 volt battery voltage back to 230 volts AC doesn't make sense. So we have a few challenges. We have the form factor. We need a small device. We can't fit a big data center box in there. We need all the plugs on the front. Extended temperature range. We have to cope with moisture, high air, humidity, stuff like that. And we have 48 volts of power. So we are not the only ones that have that problem. There also is a new thing called a cell-side gateway, because all the mobile operators want their routers pushed into the field and not just optical equipment as they did before. So in the past, it was really hard to find devices that fit these requirements. You would essentially have to go to one of the optical equipment vendors like ADVA and buy some clunky devices that are not a huge joy to use, and then backhaul all the lines to your data centers and then have them plugged into a proper router. And we don't really want to do that. So there's a new device class called cell-side gateway, and numerous vendors have them. These are the ones that we had a look at in our lab. It's basically just the same box by all the vendors. What is interesting is that all of them are using mostly the same chips. It's the Broadcom Qumran series. QAX is the first gen, Q2U or Q2A is the second generation. I would advise against going with the first generation if we want to build a new network. And they have different port options, but essentially they are all the same. And then we have well, hardware is not the only thing. We also need software. These are the software options we had a look at, and they are basically all fine, but not every software runs on every hardware, of course. There is the Arista OS for the Arista boxes, the Junos Evo for the Junos things, Nokia OS, and so on. And then we have disaggregated OSs like RT-Brick or IP Infusion that run on boxes that don't come with software. For example, UFI-Space or EdgeCore provide boxes that you could use for that. And yeah, of course, we need MPLS for our services. EVPN is good. We need atomic config reload. I can't understand why so many vendors ship OSs without atomic config reload. How am I supposed to automate these things if I have to log in and type a command and then hope I apply it in the right order? So this is a must for us. As you can see, there is one set of features that only RT-Brick has, and that is subscriber management and carrier-grade NAT. So we decided, hey, that looks really cool. We could solve both of our problems with one router, and went with the RT-Brick and UFI-Space combination because it was also, like from a price point of view, attractive. So fasten your seatbelts. We are going to use white box routers in a telco environment. These are the specific devices that we picked. The first one is the one that we would put into the concrete houses, or we call them Multifunktionsgehäuse, the shelters you see on the street corner. So that one is having a Broadcom Q2A, COMRAN 2A. It has 24, 25G ports that can also go down to 1G, with the small caveat that they don't do auto negotiation on 1G, which can be a huge pain. They have two 100G QSFP28 ports and two 400G DD ports. We don't really need the bandwidth, but I will get to why 400G still is exciting. And of course, 48 volt power, LC form factor, temperature hardened, and so on. And then there is a bigger machine that is 2 rack units and has 64 25G ports and 8 100G ports. Is essentially the same device, but with the bigger chip and more ports, and it's a full data center deep device, and has the OP2 memory expansion for the ASICs, so it can fit multiple million routes and NAT entries and everything. And what I find really interesting is that the UFI-Space full depth devices come with proper server rails, so the ones you can pull out and then you lift the device in and drop it. And I haven't seen any other network vendor doing that, and I would like to see that more. Now we have devices, we have to connect them somehow. Let's have a look at the specific challenges. So fiber capacity might be a problem. We don't have unlimited fibers available. Some POPs are better suited, some are worse. Sometimes we have to lease fibers, and every additional pair will cost a lot of money. So we need to find a way to deal with that. Big WDM systems are really expensive, and even having like just one 100G transponder costs a lot of money. So we need a few tricks. So the obvious one, we can do BiDi. We can effectively double the capacity of our fibers. But maybe this is not enough. So then there is tunable 400G OpenZR optics. This is a quite new thing, but now you can do like DWDM with passive filters without amplifiers for maybe up to 100 kilometers without like transponder cards and chassis. And they are still quite expensive, but compared to what a proper DWDM system costs, it's still peanuts. And maybe it would be cool to have something in the middle ground. And there actually is. There is LAN WDM, which is WDM in the O band, that is the 1310 nanometer range. And you can get relatively cheap WDM optics up to 25 kilometers from Flex Optics, for example, and then you can do 4 to 16 channels without amplifiers and so on, and don't have to spend an arm and a leg. And that's what we do. For example, in this POP, we have the situation that we know that we will need more than one router because we have a lot of services. We have redundant services that should be terminated on multiple routers. So we put our passive filters there. We connected our first router using the O-band WDM optics. And if we need a second router, we can just put it underneath, plug it in, done. Without having to get someone to drive out and patch cables and then drive to the next point and patch it through there until we are back in the data center. And what also could help is thinking if the double star topology of connecting all your PEs to P routers really is the best thing for you, especially if your network goes across a large geographical area. Maybe connecting your POPs in a hive pattern would be better, or running rings. We do some of these. For example, in one case, we even have like a directed RF link as a backup for one POP, and you can do all these things if you think about what the consequences are and how you ensure that not half of your internal traffic suddenly decides to route over that 1G backup link. Yeah. So keep symmetries, plan ahead, plan what would happen on the maintenance of specific devices. Okay, now we have physical connectivity, we have the routers in our racks, and we have to integrate them somehow into our existing network. And in this case, we decided to run IS with segment routing and IBGP, like one does nowadays. Just two protocols, plain simple, no RSVP, no LDP, and this also has another advantage. We already run the same stack in our wide area network, so we can just interconnect them, and now suddenly we can provide end-to-end services from, for example, some POP somewhere in Wolfsburg to Amsterdam. This was not really possible before. Before we had to have one patch in our data center between the two distinct platforms. And as a bonus point, we already have these platforms interconnected, and now we can go ahead and buy a 32 times 100G router, put it in Frankfurt, and terminate PNIs on there. We are not doing that yet, but we are almost there. RT-Brick promised to ship RPKI support. So maybe we will see the first PNI this year on RT-Brick router. And if you see sessions on internet exchanges flapping with us, then you will know Christian Giese is at fault. Okay. We have layer 2 transport, we have L3 VPNs, internet access, all fun. But then there's this BNG thing, or subscriber management thing, this mystic creature that your Fritzbox wants to talk to. And what even is that? It's actually just a bunch of protocols. So in Germany we have PPPoE. There also is IPoE, where we leave out the PPP and just do DHCP, DHCP v6, or stateless autoconf. Then we have radios in the back end to talk to some server to ask, hey, has this customer paid their bill? Are they allowed to go to the internet? What's their bandwidth? Do they have any static IP addresses or static subnets that should be routed to them? Then we have carrier-grade NAT, because, of course, there are still some people who think that we should continue to use IPv4, and so we have to do it as well. There's lawful interception, which some providers have to do, and quality of service, doing some traffic classification and shaping and prioritization on a per customer base. So what a BNG actually is doing is a customer device wants to talk to the provider, and then the BNG on the fly spawns an interface, and on that interface there are protocols like IP, and we can bind QoS profiles to that. And yeah, RT-Brick can do that, but we first have to decide, well, which flavor. I think most bigger providers run a centralized BNG architecture where they have MPLS nodes and they connect all their DSLAMs and fiber to the home devices there, and then they tunnel them to some central point where there is a huge expensive router that costs more than a house, and that does all the magic. And then, well, distributed BNG would mean we have our access devices in our outdoor shelters and so on, and the DSLAMs are connected there, and we would terminate the PPPoE sessions and DHCP requests and so on directly there. We decided to do the distributed BNG approach because first of all, we don't like big routers, we don't like line cards, we don't like failover on big routers and big failure domains, and if the distributed approach fails, we can still go back and buy a expensive machine from Juniper, and yeah. How did that work out? Yeah, we had it in our lab. It is a modern subscriber stack. It works really well. It was surprisingly easy to get the first sessions running. We found some nasty bugs, but I think that's to be expected. I don't think a lot of networks are running RT-Brick yet, so yeah, it's fine. And they were fast at fixing these bugs. Most problems weren't really their fault, but weird behavior of old Cisco CPEs, old Unify, Ubiquiti CPEs, and but we still have to support them. We can't call our customers and say, yeah, your old Cisco router is not supported anymore. I think the Bundesnetzagentur would have a word to say about that. BNG Blaster was a lot of help, debugging problems, seeing if the radio servers can handle the amount of requests and stuff like that. But if you are planning to replace your BNG or a network platform, don't spend too much time in the lab. You can't find all problems. Switch over some of your weirdest, scariest DSLAMs with the oldest devices, and you will run into problems, but after the first few, you will have it sorted out. And QoS still sucks. Don't do it. If you have to do it as little as possible. Unfortunately, for example, Deutsche Telekom forces us to do it on the L2 BSA lines. So, yeah, we have a lot of boxes. They terminate a lot of subscribers. They need config. We have to automate them. We picked a rather special approach to do that. I wouldn't say it's for everyone. Manual configuration is forbidden, of course, as one does nowadays. We use Netbox as a single source of truth, but we don't have Ginger templates or Ansible or something like that. We use a NixOS module to generate config. So we have more like a programming style to build the config trees. If you want to know more about that, you can have a chat with me outside. And then there is a small Rust tool to validate the config against the Yang models we get from the vendor. So we know if the config is valid before even throwing it against the router. And RESTconf is magic. If you can, don't bother with netconf and Ansible collections and stuff like that. RESTconf is basically just one curl command against your router, and it has a new config. Some lessons we learned over the last few years of network automation. Don't turn your network engineers into YAML engineers. YAML is not particularly a fun format, and it's still error-prone to write YAML and then create config from then. But then again, you don't want to turn your network engineers into netbox click engineers, because your first approach would be to have all the bells and whistles and knobs of your OS in netbox, and then you apply 5 different tags to an interface to enable 5 different features, and it's not much fun, and we shouldn't do that. How do we solve that? Well, we have to abstract things. We have to document descriptive. So what do we need? We have an IP address. We want to know what kind of port it is. And the rest should be automatic, because we don't want different types of configuration anyway. So this forces our engineers to not do weird stuff. In this example, we have our interfaces. They are connected to these lamps. And there's just one tag that says, this is an access port. It does PPPoE on all VLANs. That's it. And our field engineers can configure that themselves. It's getting rolled out to the routers, and that's it. Bootstrapping and maintaining devices. We can use data center tag. ONI solves this problem. ZTP, the device will fetch its config after the initial install, and that's it. And what's also interesting is that we have an IPMI in these routers. So if somewhere in bumfuck nowhere a device hangs, we can SSH into the IPMI and reset it. And we don't have to call our sister company, the power utility, and ask them to turn off the power in half of the city for a few minutes. They don't like that. CPEs is another topic. I will not go into detail about CPEs because we don't have time, and we're still working on it. But if you have the same pain with CPEs as we do, talk to me, and I can tell you about our Lord and Savior unnumbered BGP. Conclusion. Number 1, white box routing for ISPs is feasible, even for complex tasks as subscriber management. Number 2, question your existing network architecture. Don't just replace one part of your network with the same thing in modern, but think about how does it interact with CPEs, how does it interact with our subscriber databases and stuff like that. And number 3, automation is supposed to make your lives easier, not to replace fun tasks with miserable tasks. So you want to spend more time doing engineering work, and you don't want to spend all your time, staging new boxes and installing a new OS on them. So automate the miserable tasks first, and then you can have good things. Yeah, that's it. Any questions?
Thank you, Fiona, for a great talk. We're a bit short on time. I think we can take one question if we've got a quick one.
Over there.
I'm blind.
There.
Ah, da!
Hi, Gordon Guidolfavi, unaffiliated. Thank you for a great talk, Fiona. I was actually curious about the distributed BNG architecture. How do you deal with IP pool essentially being distributed, and how do you avoid IP pool wastage? Thank you.
Oh yeah, that's actually a tricky one. Yeah, the easiest solution is to carry a great NAT as a default. IPv6 is not an issue. It's just IPv4 that's annoying. Right now we give every BNG /24 of public routable IP addresses, And if we run out of public routable IP addresses, we just add another one. So because when we have a customer call and they ask for a public IP address, we give it to them. But in the future, we might switch to just statically or pseudo-statically assigning IP addresses in the radio server. And then, I mean, we're talking about a platform that can handle, what, 1 million routes, maybe 1.5 million routes, depending on the profile. So if we have, let's say, 10,000/32 routes in our FIP, then yeah, so be it. So yeah.
Great, thank you. I think we should move on because we're a bit short on time.